This is the phase diagram for lead tin. You notice that the lead forms the alpha phase and has some solubility for tin. The tin forms the beta phase and has some solubility for lead. But the two do not have a shared crystal structure. Lead is face-centered cubic, tin is body-centered tetragonal, which means that the two cannot be completely soluble in each other. Also notice that the lead is better capable of having tin in its structure than tin is lead. In this diagram, I also want to point out a few other features that are of interest. One is that this is in weight percent tin. And this is important when you look at these phase diagrams, weight percent versus mole percent versus whatever other indicator. If you get that wrong, it makes a big difference. I mean, if you think about, the weight of lead versus the atomic count of lead, that's a huge difference. Many phase diagrams will actually have a top and a bottom axis, and one will be weight percent, one will be atomic or molar percent, and both are actually fairly useful. In my work, I think about atoms and crystal structures, so I think about either molar percent or atomic percent. But if instead you're thinking about being on the factory floor and you're shoveling raw material into a furnace, weight percent is a lot more useful. It's also worth pointing out that the temperature is in degrees Celsius. Many of these phase diagrams will have marked on them points of interest. For example, here this is 18.3 weight percent tin. Sorry, this is tin, my mistake. This point is 61.9. This point is 97.8. The melting temperature of lead is 327. The melting temperature of tin is 232. And this horizontal line is 183. And we'll talk about that horizontal line shortly. Also, I want to point out that, as we expect, if you have a single-phase region and another single-phase region, between it you have a two-phase mixture. And that happens everywhere here. So alpha plus liquid, liquid, beta plus liquid, beta, alpha plus beta. Now, the kind of interesting points are, of course, the melting points, and then this entire horizontal line. This horizontal line that is called the eutectic. And the eutectic is a point in space, notably here, a particular composition. So this is the eutectic composition, which would be, say, X, S, N, E for eutectic. And this temperature is T, E, the eutectic temperature. And it corresponds to a point where a particular composition where you can go from liquid, and liquid transitions to two solids. And in thermodynamics, this corresponds to a very special point in our thermodynamic free energy space. So this is called a eutectic. If it were a solid going into two solids, like if we say we had some alpha going into beta plus gamma, it would be called a eutectoid. And again, within this set or subset of material science, there are lots of these jargon terms. If you work in the field, it's important you learn them. Those of you that are taking this as a survey class, and we've got 3 hours of lecture to learn everything you need to know, the naming is not as important as the physics of what's happening and why this diagram operates the way it does. Now, let's talk a little bit about how to think about these. And I want to point out kind of right off the bat that the method for reading these phase diagrams is exactly the same as the method we had for the, what was it? It was copper nickel. It's also exactly the same as any of the phase diagrams, right? So for example, if you're in a single phase region, it's 100% of that phase, only one phase, and the composition is exactly the composition that you have in the system. In this case, XSN star. So I'm using star again to denote the composition that we excuse me, that we put into the system. If you cool down, you cross the liquidus, and you're now in a two-phase region. In this two-phase region, at any given temperature, call this whatever, T star 1, you can say, okay, what is the composition of the two phases? And you can read the two phases from the diagram, and you get that by drawing your horizontal tie line, looking at where the tie line touches the phase boundaries, drawing horizontal lines. Again, that's easier said than done. Whew, wow. And we'll call that XSN alpha, because this is the solubility of tin in the alpha phase, and this XSNL is the solubility of lead in the liquid phase, right? This is just the same as the other phase diagrams we looked at. We then can talk about the phase fractions. So the fraction of alpha is defined using the inverse lever rule or common sense, whichever one you feel like employing that day, as this distance, the distance away from the alpha, divided by the total length. So the phase fraction of alpha in our system at temperature T star 1 and composition XSN star is equal to XSNL minus XSN star divided by XSNL minus XSN alpha. And the fraction of liquid is 1 minus the fraction of alpha. So nothing changes. The only thing that really changes is we have a slightly more complex looking phase diagram. Now, I'm not going to go through and do more readings on this diagram, but what I'd like to do is I'd like to talk about how the features in this diagram impact the morphology of the products as they solidify. So let me erase what I've written here. Okay. So I want to talk about, first, having a composition which sits to the left of this point. So this point is the point that attaches to the eutectic, and it's in this particular diagram, it is 18.3 weight percent tin. So let's go over and pick something down here that's, whatever, 16 weight percent tin, right? Again, I'm indifferent about the numbers, so I'm just going to call this XSN star 1, because it's a convenient point. So let's say you got your system, you put in some lead, you put in some tin, you heat it up until it's liquid. So we go up in temperature, and we're up there. At this point, what we have is we have pure liquid, 100% liquid phase, and the liquid composition is XSN star 1. We cool down, we cross the liquidus, we're in the two-phase region, alpha plus liquid, and because there's two phases, we can identify the phase fraction in the compositions by drawing a tie line and so on and so forth. We've seen that before. What the morphology looks like is you have liquid, and then based on the phase fraction, you're going to have some alpha precipitates that form in the liquid. You keep cooling down, you cross the solidus, and now you're in the single phase region of alpha. And what happens there is all the liquid disappears when you cross the solidus, which means that these precipitates, they grow until all the liquid is consumed, and you're left with 100% alpha, and you can determine, well, the composition of the alpha. It's the composition of the system. Now, I want to point out, again, that this is an equilibrium phase diagram, and we're just talking about thermodynamics. So we're saying that at any point I read off this phase diagram, everything has time to diffuse and move around. That means that as I cool down, the composition of the liquid and the composition of the alpha phase change, and we're assuming that at any point in time, the atoms are now in equilibrium. So there's no diffusion. It's in perfect thermodynamic equilibrium. Now I keep cooling. As I keep cooling from this, I again cross a phase boundary, and now I've entered the two-phase region of alpha plus beta. Now that means that this alpha region, it has to transform, and what it transforms to is something that looks like this. I still have those large alpha grains that I had before, but now, I'm going to pick a green here, I have little solid precipitates of beta that form. And in this region, you can say, what's the composition of the beta? Well, you draw your horizontal tie line, and you see that your beta phase is extremely tin-rich. So these little precipitates are tin-rich, and the alpha phase is increasingly lead-rich as you decrease in temperature. And it's lead-rich because the tin is coming out. So again, this is something which is intuitive. What we're basically saying is that as we cool down, the solubility of tin in my alpha phase decreases. As a result, I get precipitates. The precipitates are rich in tin, and as the tin comes out, the alpha has to become poorer in tin or richer in lead. So that's what happens as we cool down a system from liquid, and we are to the left of this tip, which is the 18.3. Now, the same thing happens if we cool down to the right of this 97.8 weight percent tin. So basically, this region and this region are going to have similar morphological behavior. Now, that leaves the regions between 18.3 and 97.8. This region is actually going to behave a little bit differently. So let's pick a composition over here on the right, and that's just to get us away from the work we've done on the left side. And let's say we pick a composition, let's pick XSN star 2. So it's to the left of the 97.8. We put our lead and tin into our crucible, heat it up. It's now liquid. And it's here. Again, 100% liquid, and we know the exact composition. We cool down. We cross into the two-phase region. As soon as we cross into that, we start forming beta precipitates. So this is L for liquid. This region I guess these aren't precipitates, these are little nucleated crystals. And there's our liquid. Okay. Now let's say that we take and we further cool down. And let's say that we stop just above the eutectic temperature. So we're still in the beta plus liquid two-phase region, but we're just 1 degree above it. So the eutectic temperature is 183. Let's say we're at 184. At 184, we can draw our tie line, and now we can read the composition of the liquid, XSNL, and the composition of the beta, XSN beta. We can use those to get the phase fraction, and it looks like it's about maybe 2/3 liquid, or sorry, 2/3 beta. So at this point we have beta that's ugly. Let me try that again. I've got beta, and then I've got liquid in between. And this is about 1/3 liquid and about 2/3 beta. Okay, now we cool down another 2 degrees and we drop just below the eutectic. So if we just below the eutectic temperature, we've transformed from beta plus liquid into alpha plus beta. And this is going to be a little bit different than what we had in the others. We now have alpha plus beta, and those beta precipitates, or those beta nucleated crystals, they stay. So I'll draw those in. Beta, 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 beta. But now the liquid's gone, and what happens is it forms what we call a eutectic microstructure. So where we once had liquid, we're now going to have a microstructure which looks like this. Where, in this case, the blue is the beta and the orange is the alpha. It has this striped pattern, kind of a lathe pattern. And this eutectic microstructure, again, I want to point out some of the language here. We call it a eutectic microstructure. A lot of times you'll hear people say wrongly, it's a eutectic phase. It's not a phase, it's a microstructure, and the microstructure is composed of alpha and beta phases. And this is what it looks like. We can take and we can read what the composition is by drawing our tie line. Turns out the beta phase didn't change composition much, right? Because it's basically the same. But our liquid is now gone, and we've just formed an alpha phase, which has this composition. XSN, let's call this alpha 2. We call this beta 2. So the alpha, the orange stripes here, those have a lead-rich composition. The beta is still tin-rich, and the fraction of the volume that is given by the eutectic microstructure is really determined by where we are in here, right? So for example, if we move more to the right, we're going to have more of the large beta crystals and a smaller amount of the eutectic microstructure. In contrast, if we move, for example, over, let me get another color here, let's pick well, let's pick a light green. If I pick a composition, say, very near the eutectic composition, right? Our eutectic composition is 61.9 weight percent tin. As I cool down, right before I cross into the I cross the eutectic temperature, right before I will have, and let me draw this here, I will have, drawing my tie line, I will have what looks like about maybe 2% beta and the rest liquid, right? Because it's right there, so actually you're having a little beta, 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 and the rest liquid. And that again comes from our inverse lever rule, right? Because the phase fraction of beta is that little slice divided by the total length. And now that I drop down below the eutectic temperature, there, those beta crystals stay. And now we have our two-phase eutectic microstructure, which makes up the balance. So in contrast, this versus this, we're able to control the microstructure that forms on cooling by choosing where we reside. And of course, if you pick a composition that is exactly at 61.9 and you cool down, through the eutectic composition and eutectic temperature, well, in this region, you have pure eutectic microstructure. So you'll have no little beta crystals, but instead you'll have all this lathe pattern. So by selecting the position, we can control if we have, at room temperature, if we have a microstructure that are large crystals with small precipitates, all eutectic, or a mixture of eutectic and precipitates, and the size, eutectic and crystals, and the size of these single phase crystals that form. So this is the basics of a binary eutectic phase diagram.